Welcome to qnawire.
In this problem, we are learning how the derivative affects the shape of a graph. So specifically, we are going to be using the first and second derivative test to determine things like where our function is increasing or decreasing and the concavity of our function. Now you might be asking, why do I need to know this? Well, this gives us a lot of information about the function's behavior, but also this is going to come in handy when you're learning how to curve sketch in calculus. This is all leading up to that. So for part A, we're given the function g of x equals 200 plus 8x cubed plus x to the fourth. Now we need to find the intervals of increase or decrease. So the first thing we should do is take the derivative. We'll take g prime of x, we'll get 24x squared plus 4x cubed. And then we can factor out a term that is common with both of the terms in our derivative. So we can factor out a 4x squared. So when we do that, we get 4x squared times 6 plus x. And then we need the critical numbers of the function. So we'll set this simplified derivative equal to 0 and solve for x. Well, x is 0 and x is negative 6. So what we see is you can plug in a point into our original function and determine if it's increasing or decreasing. And if you do that, you can see that f of x is increasing when x is greater than negative 6, and f of x is decreasing when x is less than negative 6. I'm sorry, this should be g of x. It's still the function. My apologies. Now for part B, we're told, where is the local maximums or minimums? Well, we have a local minimum by the first derivative test at x equals negative 6. So we can plug in negative 6 into our original function g, and we'll get the other coordinate. So if we plug in negative 6, we'll take g of negative 6, and we'll get negative 2, 32. So that is the point that we see a local minimum in our graph. Now for part C, we're told, well, let's determine the concavity of our function. Now, when you hear the word concavity, you should know that this is directly associated with the second derivative. You can't determine concavity with the first derivative. We need the second. So we'll take g double prime of x, and we'll get 48x plus 12x squared. Again, factor out a term to make it easier to find the critical numbers. We'll factor out a 12x, and then we'll multiply it by 4 plus x. We'll set it equal to 0, solve for x. X is 0 and x is negative 4. So now we can make some intervals and determine concavity. So our first interval would be negative infinity to negative 4. And then you can plug in a point within that interval and determine the sign of the function. And when you do, we determine that this is concave up in that interval. And then our second interval is negative 4 to 0, and that would be concave down. And then finally, we have 0 to infinity, and that would be concave up. So what we can see here is we went from concave up to down to up. That means we have an inflection point. We have an inflection point at x equals negative 4 and x equals 0. And then finally, we're told, well, what's going to happen if we graph this? Well, the information we found matched the graph of the function, and it does. You can see the graph. We see the same intervals of increase and decrease and concavity. And so this is a great way to check your work, or you can work backward from the graph also. So I hope that this problem helped you understand a little bit more about how the derivative affects the shape of the graph and how we can use differentiation to find things like the interval of increase and decrease and the concavity.